And then one day I just came across one of his public speeches where he said that, well, guys, you're arguing how it's done, but you can just look at a sample. And it struck me then, why doesn't anyone do it?
Julia Gorlova is a scientist collaborating with a group of researchers from the Laboratory of Alternative History. She runs an innovative study of microparticles left in the traces of ancient machine tools on megalithic sites around the world.
A lot can be done. All you need is to take a sample and examine it. And then he put forward the idea that if it was some metal tool or tool of some other kind, it could be worn off during the process of stone. Some traces of it should remain despite the antiquity.
The next step was to study samples from ancient megaliths brought from numerous expeditions. It was decided that the best equipment for such a task will be an electron microscope, since it allows you to see metal microparticles and analyze each of them for composition. At the beginning of the study, it seemed that the results would be obtained immediately, but it turned out that the problem is much more complicated.
We thought that we would immediately unravel the composition of the tool used by the ancients. But with a rush, it's not possible to solve. We must be honest that the method does not give an idea of the source and time of the appearance of a particle on the sample. So we have to study and exclude contamination from any restoration work that was carried out.
The antiquity of the samples, on the other hand, did not make the task any easier. The surface of megaliths has been slowly eroded for thousands of years.
So the main difficulty is due to the fact that the surface of the stone is naturally exposed to weathering, temperature changes, wind, and water. So of course it makes research difficult. But it's good that on a surface area of literally 3 to 4 millimeters, you can find the whole universe.
But despite the erosion that erases traces of ancient tools, the hardest rocks are very resistant in that regard.
But it turned out that some rocks are naturally more resistant to weathering. Very favorable was the fragments of quartzite sarcophagus. Here were the most beautiful, the most bold particles found.
We're talking about the fragments of a quartzite sarcophagus found near the pyramid of Amenemhet II. The attention of the researchers was drawn to its quality and high-quality internal angles. These internal 3-axis angles are an advanced tech element. Today, such elements are made as composition of 2 separate details. The problem is with the type of tool that did this, because you can't get such precision manually except with a machine tool.
There was mechanical processing with a tool that we do not understand now. Because the microstructure parameters indicate a very rapid impact of something, like an abrasive stone. There are chipped quartz grains. So, if you want the quartz grains not just picked out of their places, but split, you need a tool of similar hardness. And it can be some kind of abrasive with quartz or diamond but moving at a very high speed.
A more detailed comparative analysis was carried out on one of the fragments of this sarcophagus. This is an ancient treated surface, and this is the surface of the same sample treated on an industrial duty machine. The structure of the microsurface is identical. Whatever the ancient instrument was, it left traces similar to modern equipment at the micro level. The idea arose, can we get some general data on the microparticles left by an ancient tool? What if we compared dressed and the undressed surface of the sarcophagus? The peaks on these charts could represent the difference, thus the elements that were once part of the cutting tool.
We tried to catch something on the difference between the dressed surface and the untouched one. It is clear that the main part will be the material itself, from which the sarcophagus is made. but there was a hope that it would be possible to catch resonant peaks of some other elements. It's extremely hard to get the difference between them. Like on this graph, if the adjustment is carried out a little bit and the green graph is pulled up, almost nothing will be visible. The problem is that the total number of these micro-inclusions is on the verge of the capabilities of modern equipment. The hope that such a technique will be able to find anything is fading away. Although, we are using it now as a secondary one.
Plan B was painstaking point-by-point analysis of the sample's surface. This approach appeared to be the most successful. A lot of metal microparticles were found. Arsenic bronze was one of them, but in sparse, isolated inclusions. At the time of the creation of this sarcophagus, bronze must have already been known in Egypt. However, if it was just a bronze tool, the number of microparticles would have to be much higher. There also were more exotic microparticles, an alloy of titanium with iron. A similar compound is found in nature, and it's called ilmenite though. However, in the sample, these particles were with mechanical wear, and they are clogged within microcracks of the sample. Thus, they are exactly where they should stay if they were involved in sarcophagus manufacture. Titanium and iron were definitely not welded in ancient times. This is an incredibly complex process, complex even by modern standards.
We got some strange compound here: arsenic, tin, iron, titanium. All in one, so it's like fused together. Theoretically, we can imagine that there was a very strong heat and pieces of ilmenite were soldered into the bronze. We will be checking this.
But the most mysterious microparticle was this one. The researchers called it the X particle.
Now the total mystery, the X particle. The laboratory has not figured out what is it. So there's tungsten, bismuth, and molybdenum. And this is clearly in a single particle. They called it the X particle, just because such compounds are unknown. They definitely do not exist in nature. I was specifically consulted with a metallurgist.
Alloys with a similar composition are used today, where high heat resistance is required though. The melting point of such materials sometimes is up to 2,000 degrees. That's why molybdenum alloys are used in the cooling circuits of nuclear reactors as an example. From where this particle appears in an ancient object with such an explosive mixture of special metals and what exact properties that alloy could have is still unclear. Unfortunately, the size of these microparticles is such that it is impossible to quantify the composition and determine the proportions. However, it gives a chance to find something truly unknown.
We cannot get quantitative results. That's exact proportions of a particular metal. But we can confidently talk about the qualitative composition, the presence of a particular element.
It would be very interesting to recreate and test the genuine alloy though, because whatever the ancient tech was, it had simply fantastic efficiency. Take for example this granite pylon at the entrance to the Temple of the Amun-Ra in Egypt. It's quite impressive in size and almost 6 meters in height. This pylon might look like any other amongst dozens of pillars and obelisks, but in fact it is a very special one.
Here is a granite gate in Karnak. There is a decorative slot on it. Here it goes from top to bottom. There are several of them actually. This slot has a V shape, and in the depth it converges almost to zero. When you look at the edge of the slot, you don't see it. The eye is a good measurement tool. It notices up to 1/10 of a millimeter thickness. And here it is not visible. Thus it's less than 1/10 of a millimeter in depth. We simply don't have such tools.
The granite sample from this pylon was also taken into the lab. Ancient tool left an anomalous V-shaped cut in granite all along the pillar that is blade sharp on its top. It was noticed that there were some grooves inside, but by that time it wasn't clear what type they were. The results of further analysis were published in the international scientific journal Universum. It was discovered a clear system of parallel grooves that goes parallel at all the length of the cut. Moreover, the tool used left grooves of the same depth no matter what media it cut, feldspar or quartz. For researchers, this was hard evidence of a machine tool with some type of fixed abrasive at work. But what tool and what abrasive though? Initially, everyone thought that it was some kind of a disc saw, but apparently the instrument was rather more mysterious.
Here the grooves are visible. To our surprise, the grooves remained parallel to the edge. If it was an angle grinder, it would leave concentric circles. There's nothing like that here. Here, the grooves go along only. There was a feeling that this as well, some kind of fixed abrasive. Well, again, if it was the abrasive left, then what was it on? But when we are talking about the fact that this gate is 6 meters high, so what kind of saw was it? Where the cutting edge went to 0 millimeters. This is generally nonsense from the point of view of physics. And because of this height, the question arises. Well, not circular saw, not straight, because the height is 6 meters. How can we physically come up with a tool that left parallel grooves? Well, the only association comes, it's some kind of a knife, which cut the granite like butter somehow, and left this type of grooves.
The other thing is that the type of microparticles in a sample were similar to metal shavings.
There are some particles that look like metal shavings. There are a lot of such. There are a lot of them in Karnak's sample. Thus, accidental entries can be excluded. This predominant alloy is bronze with a kind of meteoric iron, but we have not proved it yet. The composition is similar, though. Andre, in my opinion, believed that the working tool was made of this alloy. And the sample is full of these microparticles. So it was that alloy, yes.
The first results were quite puzzling. The microparticles left in this sample from Karnak pylon looked like an unknown bronze alloy.
There are copper microparticles, but not as pure copper. It's in different variations there. And again, when copper and iron came across, some opponents of research began to rejoice, saying it's copper all the same. Copper, but as far as I know, not in such compounds that were known to the Egyptians. Moreover, this alloy is repeated at many different sites and many countries. At the first glance, it's a bronze, but not with a tin only. It's with significant admixtures of iron, nickel, and cobalt, saying that this is obviously not ordinary bronze.
Or maybe it is not the matter of an alloy itself or the tool, but some technology of unknown origin.
Let's assume for a second that the ancient Egyptians made some kind of diamond or, at least, quartz coating on copper. Somehow, they fixed it there. Imagine how it could be done at all. But the question is, how did they do it in terms of technology? And how did they move the instrument in the way where the surface is generally polished? It is very, very smooth. Granite has been removed by a machine tool. This cannot be done by manual processing.
Andre further developed this version. It was this alloy that he tried to recreate and a successful patent. Again, these experiments have stopped since Andre's death, but the first one seemed to be unsuccessful. He said that something was not working there.
These were not the first experiments that failed in trying to restore the ancient technologies. Some researchers described their unsuccessful experience with alloys that seem to have been described in great detail. Trying to understand the reason for their failure, they realized that mistake was because a flux used was chemically pure, whereas those the ancients employed were impure. For instance, salts obtained from natural products and consequently capable of provoking catalytic actions. The latest research shows that the hardness of certain bronzes may be modified by carefully applied heat treatment, but the range and variation is not great. And as modern apparatus for governing the temperatures is absolutely necessary, the method would not be available to the not advanced civilizations. There is, however, little need to spend time to find out hardening processes that might have been applied to bronze, because works in hard stone were carved during the extensive lapse of time prior to the introduction of tin into Egypt, and therefore the question is limited to the hardening of copper. Such an unusual alloy of bronze is found on many ancient samples, complementary with traces of machine tools that do not fit into the official history at all. The number of metal microparticles varies from sample to sample to the degree of a complete absence, even though the tool marks suggest they should be. This led to an idea that some technologies were used for which metals played a secondary role.
If there are no metals, then I can only think about some technology, according to our modern level of development, which are composite materials. The composite materials have a silicon and carbon and some sort of base. Silicon is not a metal. Carbon is not a metal, so it should not give any signs in these studies where metals are detected. But this is still such a semi-fantastic option. All in all, it will be necessary to somehow prove it and show that it were the composites used. It should have some kind of adhesive base that should also remain. And composites are not eternal, they also wear off. Despite the fact that we already make materials that are even harder than a diamond.
We are also thinking about non-metallic technology, but here my qualification is not enough. Here you need another specialist, another profile, not a geologist. I remember at one of the seminars that a specialist in physics said that perhaps we are wrong to think that these are the remains of a metal tool. Here he put forward the idea that metal microparticles are a side effect of the tool, working on some other principle. And then there was an unusual particle, and he said that such microparticles are formed as a result of low-energy nuclear reactions.
The idea of use of advanced high-tech methods is not accidental. There is a clear presence of technology that cut granite like butter and might be based on physics that does not yet make sense to us. Very often near the metal microparticles, very unusual formations were found, spherules. In conjunction with the microparticles of heat-resistant alloys, this might indicate the use of a completely genuine technology that was not based on the casual sawing.
What are such formations interesting for? They appear at a very high temperature and heating rate and instant cooling. They are formed at such rapid temperature changes. And these spherules sometimes are of cosmic origin, and they are also tech origin. For example, from welding, grinding, or drilling metals. Here again, we may be led to think about the side effects of using the tool.
On some examples, for example in Baalbek, there were too many of them as for natural sources. In this picture, there are 3 of them at once on a centimeter of the treated surface of the megalith, whereas space dust, for example, would give only 3 spheres per a square meter. It turns out to be a paradox. On the one hand, we see the presence of bronze alloys that in general aligned with the capabilities of ancient people. But on the other hand, the results of use of these tools are absolutely superb and mind-boggling. How could it be explained? Can it be, in fact, that the technically advanced civilization that built the megaliths throughout the world at a certain point of history reached the highest level of technological development and experienced destructive contact with some external force? An irresistible power that interfered with this progress and successfully stopped it. Colonel Harland, in his work on the metallurgy of ancient Egypt, suggested that iron metallurgy was known to the Egyptians much earlier than it was generally accepted. There was even a special term for it, metal of heaven, and it was depicted in blue, in contrast to bronze and copper. And he noticed an interesting thing. Its use in ancient times was forbidden by religion. That's why the majority of antique objects found in Egypt are recovered from tombs. No articles made of iron would be placed in them, and thus the sources that yield the bulk of our articles in copper, bronze, wood, and other materials. If you make the process of religious prohibitions stepwise and stretch for thousands of years, it will be absolutely destructive for practical knowledge. In the Bible, for example, this approach was taken to the next level, till the complete prohibition of the God Yahweh of the technology of dressing stone as such. Already called it nothing but defile of altar if one uses a tool on it. Nevertheless, fragments of high technical knowledge made it through. From ancient treatises, there are known instructions on the seemingly absurd preparation of metals. Some historians affirm that since endless repetitions of the process of refining and purifying metals and metalloids do not in any way alter their properties, the recommendations of the alchemists in this connection could only be considered as a kind of mystic lesson in patience, a ritual gesture, like telling the beads of a rosary. And yet it is by such a refining process and the technique described by the alchemists known today as zone fusion that the germanium and silicon used in transistors is prepared. We know now, thanks to the work done on these transistors, that by purifying a metal very thoroughly and then introducing minute quantities, some millionths of a gram of impurities carefully selected, the substance thus treated is endowed with new and revolutionary properties. Of course, a knowledge of this kind requires a serious level of development and understanding of metallurgy and advanced science in general. And they had to belong to a technically advanced civilization, the search for knowledge of which will continue.
These are things that certainly amaze and make you think about what kind of tools these were. Can we understand them, and can we somehow repeat some analogs? And here is a moment that I personally really like. We get the opportunity to translate history from the descriptive science of the past into the productive science of the future, and try to find these technologies